Swayam Prabha. Digital India. Educated India.
So let me introduce the speaker, Faisal Irshad Khan. Faisal Khan is a professor in Chemical Engineering Department at Texas A&M University. He is also director at MKO Process Safety Center and Mike O'Connor 2 Chair. His research interests include offshore safety and risk engineering, offshore asset integrity assessment and management, process modeling and system design, offshore environment system modeling and management. He has vast industrial experience, as part of which he established a multidisciplinary center of excellence at Memorial in the position of director and facilitated research that led to new technologies as the Canadian Research Chair Tier 1 Offshore Safety and Risk Engineering. He has been bestowed with many awards and honors. The recent ones include his induction as Fellow of Canadian Academy of Engineering in 2021 and in 2018 as a Fellow of Engineering Institute of Canada, and in 2017 as a Fellow of Canadian Society of Chemical Engineering. From 2011 to 2014, he was a member of the US think tank on process safety and risk management. Okay, over to you, Professor Faisal Khan. So one day I did my postdoc in Texas A&M University, so I was not thinking of that time was COVID. All right, over to you, Professor Faisal.
Thank you. It's very good morning from the place where I am, and very good afternoon to those who are staying from southern part of India. To friends in Chennai and neighborhood, Vanakkam, and very glad to be here, and thanks to Professor Raj for giving this opportunity. I am currently in a very nasty COVID, so if you see my voice trembling or observe a fatigue, please forgive me. I'm just in the middle of a very bad health condition. So because I committed, so I thought I should share some thoughts with you. And Chennai happened to be my favorite place and a long-standing thing, so I just can't refuse to get connected. What I'm hoping in the next few minutes is to briefly introduce you some fundamentals which perhaps will or may challenge you because the way I perceive safety is somehow out of book concept and may not be well aligned with the concept you might have come across either in the textbook or in some way of industry practice. I'll briefly touch upon what's happening around us in terms of modernizations and digitalization and where does this offer us challenges and opportunities, and finally introduce some potential solutions. So the way I see safety is it's slightly different, as I mentioned, and to me, I began asking myself, what is safety? And this is way back in late 80s and early 90s when I was a graduate student back in India in the same neighborhood. So questions remain to be, what actually is safety? And the way I, over the last 30 plus years, was able to answer is to relate it to something that is very dear to my heart or to many of us, is health. Means if I ask the same question, what is the health? We all tremble to define it and qualify it. But we do have a very meaningful, personally attached connotation to it. And that is, we consider health or remain to be healthy is being away from illness and sickness. And the same extrapolations I use to connotate the safety, which is an absence of incident or unwanted situations. So that's how we could able to analog ourselves into how we believe to ourselves being remain healthy, being away from a unwanted sickness or illnesses. Likewise, from a safety perspective, as long as we keep our systems away from incident or unwanted conditions, we can consider to be safer. Then, of course, how do we measure it? Well, there's no meters available either in pharmacy or so matters in our industrial outlook catalogs where they can able to go and plug in into the plant or plug in into our body and say we are 80% healthy today or we are 80% safer plant today. This all depends upon measuring these conditions that will make us to get unhealthy. And they bring us closer to what we consider in qualifying term as risk factor. So today, most health alignments are measured or qualified and communicated to the patient in the form of risk. For example, if I walk into a physician, they will make a bodily measurements, they carry out series of tests, and towards the end, they will attempt to qualify me or communicate with me saying, well, that can probably you have the cardiac arrest risk factor of 40 or whatever the number or connotations in a particular region follows through. So what happens in that process is that a series of measurements being taken, interpreted in a combined inclusive way, and finally a message is conveyed to the individual. The same approach is being recommended for industry to follow, being able to identify, monitor conditions that could lead to unwanted situations or potential incidents. And the closeness and farness of that particular conditions is what we qualify to be the risk. And that way we are able to communicate one unified parameter to our both industry senior colleagues, executives, and also in a greater sense to the public. Because public understand these risks to their own personal connotations, as I mentioned from a health point of view, they can also easily correlate that from a safety perspective. Now, having known what is causing us to closer to these risk factors, we can now make efforts to minimize them by virtue of taking actions that help us to keep them away and develop a monitoring systems as we do in our health today. Knowing that I have a potential of cardiac arrest, my food habits changes, I monitor more of blood pressures and number of steps I'm taking and all other parameters. To do what? To measure and monitor my health conditions by virtue of a common unified parameters I'm conveyed with the risk. So trying to minimize it and maintain at that minimal level. That's what we do for our own individual health and community health when we talk about situations like pandemic, which we are going through. The same concept is well applicable to the industry if we are able to take that so personally and able to evolve the science supporting this and then engineering able to implement it. So my simple message to all of you, being an audience, is safety to the system is a health to the human. And if we can relate, believe, and practice, we will be in a different working environment. How do we actually measure that? So I did connotate that risk is a unified parameters that help us to connect this. But in order to relate that in a positive sense, which is because safety, like health, is a positively connotated term, risk is virtually a negative term, we have inverse correlations. So we can able to quantify risk to a greater extent as we do in our finance business. We go up to the 2 significant decimals to quantify risk for any particular venture or investment or projects. We could use similar rigor to qualify and quantify risk related to a potential incident happening. And these risks can directly then convert it into the safety factor by inverse correlation. That means we can have a quote unquote a unit that defines us in terms of a scientific value, both in quantitative terms and a unit term. And that way we can able to now focus our engineering efforts to minimize it. So this is all well good in last 10, 15 years. That's where being practiced. That's where some of the North American industries had started to implement as my learned colleague before talked about process safety management. How do you then implement and be able to unify these all 14 elements into a cohesive form so that senior management able to relate risk is the framework that has been what adopted. So with that background, once we move into today's time, when we are talking about digitalizations, automation, that what simply means that all of our operations as we speak are all interconnected. So the same processing unit that was a batch mode in 70s now start to operate in continuous mode, but highly integrated with instrumentations. And these instrumentations, earlier days, used to be controlled through a pneumatic control, but today, through the electronic systems, can all be integrated and remotely controlled, remotely operated. This is a phenomenal opportunity from an automation perspective and being able to operate regions where we can never be. One example is I'm in front of you today from 10,000 plus miles away in a time zones where you wouldn't be deeply sleeping. But all these are greater possibilities that has unlocked due to these so-called digitalizations and communication permutation. But it does add a complexities. It does add the unknownness into our systems. And these unknownness are often being the source of recipe for causing disaster. So while we have a greater advantages and benefits and all these, which I'll leave to my colleagues to talk about, I'm looking into a microscopic view and seeing what are the new, quote unquote, new challenges are getting introduced as we embark on this journey. And this I would explain in a very simplistic way, and please forgive me if I touch upon some of your sensitive points. One of the core challenges I'm observing with the colleagues and friends and in the friends in industry is very generalized and broad brush type of interpretation. And what the interpretation is that people thinking that putting sensors, putting controllers means we have achieved a greater depth of understanding and automation. And that directly relates to the process systems operation. Unfortunately, that's not how I see it. To me, in a simplistic way, by creating observations, by virtue of simply putting a sensor, is not what it means, the digitalizations. And observations can easily be created by a sensor, but till we qualify this with a unit, what the observation is about, it doesn't have any meaning. So simply having a thermocouple give you an electromechanical or electrothermal signal, and that could be a digital form, maybe 32. But what that 32 means, is it a Fahrenheit? Is it a temperature? Is it a pressure? So qualifying that unit is an important aspect. So we're getting observations out of the sensor, but they need to qualify. And this qualification happens through the data. So once we have these 32, we qualified it to be degrees Celsius. Now it became a temperature, which became a data. But what does that 32C mean? Is it good, bad, ugly? Is it warm, cold? What does that really mean? That needs to be interpreted. And that's what, once we have the 32C and able to interpret that, that becomes the information. So being able to say 32C is hot in a given context, then that becomes the information. So you see, putting a thermocouple is not making directly, it's a starting point, but the thermocouple need to qualify the electrochemical signal into the unit. That unit need to further qualify into information. And it's that information, when we are able to use and reuse it by virtue of memory or by virtue of the mathematics formulations which we built on that, then only it becomes a part of the knowledge. And that's where it starts to become more meaningful. So my dear friend, this is where we have challenges. By simply putting or creating observation does not mean we are building knowledge. There is a lot more need to be taken in between these two. And that's where my greatest and biggest challenges are we, as a scientists, engineers, and our next generation, equipped with set of mind, tools, and techniques that enabling these transformations from observations to data and to information and subsequently to the knowledge. Because if we do so, yes, we are then in a very different war front, and that will enable us a greater success and a greater safety. Example of that in the processing systems, we often use, if we go to the literature, we find a lot of tons of work being done in the last decade or so on the process monitoring. being having all the soft sensors and others being developed, implemented, and they all help us build the knowledge in the form of using a control and system theory. And this knowledge is what we subsequently use to build safety systems and enable that practice. And these safety systems operate, as we expect, to be in a predictive mode rather than assistive mode. That means we are able to foresee unwanted situations evolving and able to take action before these conditions go in a form where we feel discomfort. And that's the greatest strength offers if we do things right. And that's where I'm encouraging all the young colleagues to work on providing these prognosis-based approaches that help us to be equipped with the methods that enable us preventing incidents rather than assessing and managing them. In order to do so, what are the key challenges? One of them is what we all have practiced in the last 3 decades. Means during early time, this is where I spend most of my early research, is developing these risk models, which help us bringing down the risk from an early design, conceptual design, all the way to the feed and subsequently to the installation. That's what happened in 17 and 80 with great success. Today, in any energy industry, you wouldn't change a bolt without having a risk assessment done. But this is all good because this all believe that once we have assessed risk and take action, they will remain so. In a simple word, if we had designed a safe car, that means it will remain safe on the road. That's today's context, a very poor assumption. Because the systems are failing not because they were designed badly, it's because operational envelope has changed. As my learned colleague before said, the industries are pushing to the limits, and some of these constraints are not anymore holding valid. And that means we are observing risk even beyond what we in fact envisaged when we had the conceptual design or early phase designs. So this risk, which was earlier and I used as a means of design, has now exceeding far more threshold than we ever envisaged. And this is simply because of the operational changes and operational division. So how do we model risk as a function of time and space remain to be a challenge. We have made significant progresses in our both science and basic science and applied sciences, which is bringing us phenomenal benefits. Now, these works are dominant in a particular sector. For example, we have today used a lot of molecular dynamics-based approaches to study even the smallest possible atoms, both from a safety perspective in some of my colleagues and my research, but also in a broader sense from efficiency and all other parts. The challenge remains is scaling up these molecular dynamics-based or quantum chemistry-based approaches result to the field size or supply chain levels. Means looking into a possible hydrogen production at a particular site in a catalyst all the way to think about how this particular hydrogen is going to be transported in community through a supply chain. This is scaling up is the greatest unknown and the biggest challenge as what we are facing humankind now. So that requires a very broader understanding that as we are investigating challenges at a one particular stage or level, we need to be mindful that this requires scaling up and that unknownness need to be addressed while we are working on. Then second important challenge we are all facing together is the complexity. So while we are all greatly benefiting the flexibility offered by the remote operations, digitalization, it introduces a new set of challenges, a new set of vulnerabilities, and these are never seen before. I mean, for example, one could able to control house temperatures from the home office, can video feed it to me who has fed the dog and where the cats are in a given day, an hour in the day. But the same feed can also be easily interrupted and someone can open the door without even coming home. Someone able to open the excess heat in the house without even entering into it. So all these new dimensions, greater flexibility, but equal challenge comes along with it. And these are complexities that simply is not the IT issues. It's the issues that are process dynamics that we need to understand and build a robust barrier around them. And the last but very important, as Einstein said, there are only two certainties in the earth in the living being. One is the death and other is the uncertainty. So we are living in an uncertain world, and these uncertainties are compounding as we getting more and more ourselves engulfed into more complex engineering systems. Not to say that it's going to change anyone, is what we need to is adopt and try to unleash these unknownness or uncertainties. As I mentioned before, is by creating these data into information and subsequently building knowledge, if this is how we are able to unlock some of the mystic knowledge. And that's how we address this uncertainty. So one possible solution that my team has addressed, particularly one of the challenges you saw about the risk, and particularly risk as a function of time and space. So some of my students over a period of time have built upon what we call operational risk management or dynamic risk assessment and management approaches, and we have widely practiced these into the different cases. So what I'm hoping to do is next 5 to 10 minutes illustrate you that how these have been successful and where they can easily be adopted. So these dynamic risk approaches are assessing the risk as a function of time and space, and risk happen to be a predictive term. That means we are looking for today and seeing in time in horizon with the time step 1, 2, 3, depending upon how far we want to see. And these dynamic risk models are built upon the system. So they are not simply based on what we call first principles, but they are based on the logical systems, which initially started in the late 90s or early 2000, which was more of a graphical approach used, is now a common practice in the industry called bow tie models, where you can able to relate the incident causations into the effects. And that way you can pictorially represent how the change in the variable X would potentially cause a leak or a PSV lift up, which potentially cause a release scenarios. So being able to relate that and monitor and continuously update based on evolving condition in the plant gave us a very good understanding of evolving risk in the scenarios. That helped us significantly over a period of time. But as we move into more digitalization, where we have far more data coming in, that means we can relax some of the logical assumptions which we made earlier in terms of their dependency, and now use what we call network-based approaches. That means some of these dependency assumptions which we are constrained within our graphical method earlier are now relaxed. So it's more of an interconnected variables that may not necessarily to be linearly dependent, but non-linearly codependent on this could easily be modeled. So that provides us more robustness now in our ability to be predictive, and of course increases precision in our risk assessment. Now, using these approaches, we can able to use the both existing real-time data coming from the processing systems to build these models, and these models, once you have, are equipped with what quote unquote the knowledge. So they are not black box models like artificial neural networks and others techniques. These are knowledge-based systems. That means they are capturing the physical variables in its connotations in a physical dependency, qualified with the physics of the system, rather than simply a black box of correlationship between the variables. We are also able to model a high level of dependency in a probabilistic framework. That means if A is changing and A is dependent on so many more parameters, how they will be affecting it. So that provides us a very good, robust framework on a database system, which we could able to create a knowledge-based framework and use that as a tool to model risk as a function of time and space. We tested that in the two different sets, which I'm hoping to present to you, but it has been widely reported in the literature for many range of examples. So one, which is a well-known example in offshore, which is where I spend most of my time, is Macondo well. So we tried using a earlier proposed approach of a graphical, means bow tie based model, and trying to predict using publicly accessible data that could or should we be known that there is a potential evolving conditions in the wellbore as we were drilling through into Macando? And the answer of that particular analysis using the data available in public domain and the model approach, the answer is yes. The accident based on the real-time data coming from the wellbore, able to model the risk, which we talked about briefly, and we would have known 21 minutes before the disaster happened that risk had gone far beyond the limit that industry could be or would be able to handle it. And that's clearly visible here in 1936 as you see the vertical risk line going up. So, my dear friend, the concept I'm sharing with you is nothing new, so-called something that can be award-winning. This is something what in different shape and size our stock exchange industries widely uses fluctuations and model them into database data-driven systems to fluctuate what risks are going to be in a particular share. It's just that their approaches are slightly driven based on the number, which is the dollar or particular commodity. Here we have to consider system dynamics, that is the processing system, but it's a very similar approach. So what it simply tells us, yes, if we wisely use our existing knowledge and the data coming from the system, we can update risk and we would likely to know how and where the situation could go bad. And that's built a lot of more trust in these approaches. And I'm sure these will become the part of day-to-day operational tools in the industry to come. Testing this into the lab to ensure that we have better management and able to find what my colleague was talking before, a root cause analysis, that can that be done in the diagnostic form, just not in the prognosis form? Answer is yes. So if we are able to assess risk and if risk is seen to be unacceptable, can we put a just like how we do in a phone and put a tag and say why it is red, and can that trace back to the source and see what variable is actually making this to go red? And that is, in simple answer, is possible. We tested that in a distillation column in our lab where we intentionally introduced a variation in the feed rate and able to model the system and then diagnose that once knowing that there is a fault, and the fault can easily lead to a high pressure system activated into the distillation column. We run the diagnosis and able to very clearly see, as you see red block here, we're identifying feed rate to be the main source, which exactly what we did. So yes, we did know what would change, but we also being able to model that using the system we have. And we have tested this, and when I say we means is the students, those who are brilliant and outstanding, have tested this on a range of case studies and able to communicate that in wider public. So my simple answer is yes, dynamic risk approach provides us a robust mechanism that helps us to build a processing system that addresses some of the challenges we are likely to see or we are seeing in our process system digitalization. It helps us or enable us in many ways to implement what Professor Kurz has talked about, inherently safer design and operations. So if we use the technology in its right phase and shape, we may be able to continue evolving with it and making sure that we remain safe as we move into the new era. With this, thank you very much, and I'm happy to take any questions you may have.
Okay, thank you, Professor Faisal Khan. Any questions from the audience?
Hi, Mr. Faisal. I'm on from Institute of Investigation. I just want to have some idea about how to fix the basis and assumption in order to predict the failures of any unit operation, mainly for the processing facility. So that based on that, at least we can come up with what are the proper safeguards to protect our asset. Thank you.
I'm not sure I understood the question. So if someone can help me explain, then probably I may be able to respond.
Right, I want to understand because you were highlighting just now about to predict the failures. So we don't need to. Can you hear me?
Yes, I can hear you, but yes. So I was emphasizing what that part I missed.
You can speak slowly and
Okay.
Yeah.
So in order to predict the failures, all right, so we need
Yep.
some basis and assumption as an input in order to predict those failures for any particular unit operation our processing facility. That by having all these basis and assumption, yes, which will help us come up with proper safeguard to protect our assets. So my question is that how to get or how to fix the basis and assumption in order to predict all those failures. Because from this process safety digitalization, it will something like a bit more advanced compared to typical that we do hands-off in industry. So this is something that we are predicting some failures. So there's a reason I want to understand about the basis and assumptions that we use. I hope.
Good. And no, I understood the question now. Thank you. Thank you very much. And my apology for having difficulty in following. So, okay, my dear friend, let me explain you in a very simplistic way. HAZOP is not a problem-solving method. HAZOP is to identify the challenges one would see through our broad experiences of similar systems. So this is relying on to our experiences and doing this jointly. So let's park that for a minute. The way the benefit the digitalization brings is being able to relax the sum of assumptions. And let me explain how. Imagine if I have representing a pipeline failure based on the historical data I have collected over a period of time from a system, is y is equal to mx plus c. Now, this particular equation will give me the idea, if it is a function of time, when is likely unacceptable probability would be in a leak or a release. And this is based on the historic data we have collected from the same pipeline system. But remember, the accuracy of the prediction is totally dependent on this particular equation which you are using, which we know are only limited because it has only a limited data. What digitalization helping us today is that we do not have to hold this equation valid as a gospel, but use that as a starting point. And the sensors or the data available from the pipeline able to improve the parameters which we are using in this equation. So y is equal to mx plus c, the m and the c could change depending upon how the system is deteriorating. That means the last year, the m could be different, but based on your current observations from the system, and what these observations could be is temperature, pressures, and other variable, the m might change. And because the m change, your chance of release has changed, which if you do not have the real-time data coming from facility, you wouldn't be able to relax this assumption. So, my dear friends, in digitalization-based systems, we have to utilize the information which we are collecting through observations and data for using the model just like I mentioned, and improve this continuously so that you always remain ahead of the game. That's how you are able to use your data to predict and use the prediction to improve the system. I hope I attempt to answer the question.
Yeah, thank you, thank you.
Any other questions? Yeah.
Because as you mentioned, Bayesian models were able to predict the risk associated with the process dynamically. So just this is not a okay. So this is not a question. Maybe I was just wanted your opinion. So you mentioned that previously that the Bayesian models were able to predict the risk associated with the process dynamically. So what do you think that if we incorporate the risk associated with the human operator who is handling that process dynamically? So can the risk be reduced when we incorporate the behavior of humans?
I'm not sure I understood it, but I'll try to attempt answering this. So, Bayesian network-based approach is not limited just to the engineering system. They're equally applicable on the human factor performances. So, if we simply say a controls, I'm simply giving an easier example. Let's say I'm driving a car. So as a driver, I have human factor associated errors. These errors can easily be modeled using the Bayesian network or knowledge-based networks approach. And based on my day-to-day conditions, the parameter of this network model could be improved. That means yesterday, based on my mood, my chance of making an error was 1 in 100. But today I'm better equipped, or I'm sharper, I'm behaving better. My chance of making an error is 1 in 1,000. So imagine same person, same task, but because you have collecting the data around the performance shaping factor of individual, and these are changing depending upon of the day or individual is involved, the chance of making an error is changing. So that's one aspect, that's a human behavioral aspect, which now can easily be embedded into the system. Likewise, just like I talk about human, we could easily embed that into a processing system point of view. So having sensors which tells them the real time both process operational variables such as pressure, temperatures, and others, but also integrity variables such as the strength, the strain, and other parameters coming real time, can give us the process model in terms of its likelihood of failure. And these all can easily be adaptable both the changing condition. So Bayesian or knowledge-based framework provide this broader opportunity to integrate both soft factors such as human, but then hard engineering concept like stress, temperature, and pressure into a unified framework.
Okay, so like I have one question. So one or two questions in that. So what's the good window? Say for example, if you keep the window very long, then the update is like not much. But if the window of past measurements is like very small, then your model will be very sensitive. So what is a good? Does it depend upon process, or are there any heuristics? And I have one follow-up question too. So I work more in controls. So say there is a MPC controller in the plant, which is also dynamically getting updated using the past measurements. Then how this would work, because controller may automatically control some trends. So
Good. So my simple answer to your very, very intelligent question would be that your update should not be higher frequency than your control actions ability. So in my view, the update should be of the same order as that of your control action. Even simply saying, if the currency denomination is $1, having an accuracy or representing the value of a finance transaction into $0.5 doesn't make sense, does it? Because the lowest denomination available is $1. So, in my view, there is simply because computer give you a umpteen digit of accuracy doesn't mean that anything. The accuracy is the lowest order you could able to action. So my dear friend, the simplest and the easiest effective answer is the update should be based on your control action possible. Now, if you wanted a is slightly higher sensitive, it could be the order divided by 2, but that's the maximum you can think about. That's a very simple and perhaps a direct answer to your question, sir.
Thank you, Professor Faisal Khan. I think time is up, so we'll end the session, and thank you very much again for your talk.
Thank you all. Wish you all very lovely evening and enjoy.